So we're talking about conditional probability. And we're going to introduce a new kind of symbol here, this vertical bar. Whenever you're talking about something inside of a probability statement, this would be the probability of an event F given that an event E has occurred or is the kind of true nature of the situation. There's a couple of ways you can compute that. It can be the number of outcomes common to both E and F divided by the number of outcomes in just E. Now, notice that E is the second thing. It's what's given. It's what comes after the bar. And thus, it is the thing that's going to be in the denominator. So that's kind of an important link here. Another way to write this is you could say it's the probability that both E and F take place, divided by the probability that E takes place. Maybe I'll move that down so it's a little easier to see. That's another way to formulate it. So you can either just count the number of outcomes in E and F and divide by the number of outcomes in E, or you can calculate the probability that both E and F events occur and divide by the probability of E. And so maybe we'll keep this in mind here. Let's try to actually compute a couple probabilities of this nature. We'll keep this thing up here, potentially using it. You are dealt a card from a 52 card deck. So here's how it's going to work. I'm going to deal you a card, but I, the dealer, I'm going to look at it real quick. I'm going to take a quick peek at it, and I'm going to see what it is, what kind of card it is. So I get the card, and I see that it's a red card. I can say, okay, it's a red card. So I tell you it's a red card. So suddenly that completely changes the game. Now, before you look at the card, you know it can't be a spade or a club. Essentially, I've knocked basically half the possible cards out of the deck. That is what I've done. So what we need to do is we need to essentially, using this formula or going up here and using the number of outcomes in each, the answer, find the probability of getting a heart, given that the card you were dealt is a red card. Well, that's going to be found by doing this calculation. You take the number of cards that are both red and heart. You take the number of cards which are both red and a heart, and you divide by the number of cards that are red, the thing that you're given. In this case, so that's going to end up being, well, the number of cards that are both red and a heart card is just the number of hearts in the deck, because hearts are automatically also red. So that's going to be 13 cards in the deck. And you divide by the number of cards that are red. Well, half the deck is red. Half of 52 is 26. And so 13 over 26 actually reduces to 1/2 or 0.5. There's a 50-50 chance. If you draw a card from the deck and I tell you it's a red card, and I'm not lying or anything, it is for sure a red card, then you're not looking at the entire deck. You're just looking among the 26 red cards. Half of them are hearts. So there's a 0.5 probability that you're going to get a heart, as long as you know that you're getting a red card. Now here, what we're given is that the card is a heart. So the probability calculation here is going to be, again, the number of cards. If we want the probability of getting a red card, given that it's a heart, it's going to be the number of cards that are both red and heart. Same as before on top. On bottom, though, since we're given now that it's a heart, the bottom is just going to be the number of cards that are hearts. The number of hearts in the deck, basically. So this top number, the number of cards that are both red and a heart, is still 13. But this bottom number, the number of cards that are hearts, is also 13. So this is just 1 or 100%. Now let's think logically about that. If I pull the card out, I'm the dealer, and I know, or I tell you that it's a heart, then the probability that you're about to get a red card, well, if you know it's a heart, all hearts are red cards, so it's a 100% chance you're going to get a red card. And that's exactly what this probability calculation demonstrated. So it just kind of makes sense how conditional probability works in that manner. Perhaps we could do number 3 here. What is the probability you're getting a jack, given that the card you're dealt is a face card? A face card is a jack, queen, or king. Because they have actual faces of people, if you will, on the cards. Well, let's think about it. There's 4 jacks, there's 4 queens, and there's 4 kings. A third of the face cards are jacks. So if I tell you you're getting a face card, that's for sure happening. Then you should think there's a 1/3 chance it'll be a jack. And yeah, that's exactly what it's going to be. This probability calculation is going to be the number of cards that are both face cards and jacks, divided by the number of basically just face cards, because we're told that we're getting a face card. Well, the number of cards that are both face cards and jacks is going to be 4. It's the 4 jacks in the deck, because they are both jack and face cards. The number of face cards total, 4 jacks plus 4 queens plus 4 kings, is 12. So there's a 4 in 12 chance, or a 1/3 probability, 0.33333, 33.3333%. Yeah, if I tell you you're getting a face card, a third of the face cards are jacks, so there should be a 1/3 probability that you're going to get a jack. So conditional probability, that formula seems a bit mysterious, but it's actually not as bad as you think. Now, one of the best places that we can look at conditional probability is in these kinds of 2-dimensional tables like this. Let's say you have a sample of 232 total people. 232 total people were sampled. And either we look at their records or we just ask them questions. 64 of those people are currently married and are male. So this means 64 means they're married and male. Notice the word "and" in there. 2 of those people are widowed and male. 9 are divorced and male. 129 total are married out of the 232. 31 are female and have never married. So what we need to do, we're going to compute some conditional probabilities. Look what is given. You are given that the person is divorced. So you're not looking at every column here. You're actually just kind of looking at the divorce column. And you want to know, essentially, if I pick a divorced person, someone who is known to be divorced, what is the probability they're female? Well, the top number is going to be the number of people who are both these things, female and divorced. That's 13. The bottom number is going to be the total number of people who are divorced, the total number of things that are in the given category. So there's going to be a 13 out of 22 chance. And then you can go and calculate the decimal or whatever you need for that particular problem, round out to as many decimal points as you need. Now let's look at this next one. It wants to know if we select one person at random, find the probability that the person is divorced given that the person is a man. So now what we're given is that they are male. And males then comprise this row here. So we're not looking at the entire table anymore. We're just looking at the males, the men. There's 112 total men. So that's going to be the denominator of our probability calculation because we are given that the person is a man. So it's going to be 112 on bottom. And then the top number is going to be both the number of things that fit into both of these categories. Is divorced and male, that's 9. So whenever you're given some information, you're suddenly zooming in on just one specific piece. You're not looking at the entire 232 people per se. You're just looking now at the 112 people that are male in this particular problem right here. And then you can do this probability calculation. You have calculators, do 9 divided by 112 and round appropriately. Zoom out a little bit. So this one's going to be really interesting. You may have heard a lot of people coming out and talking about how, say, you have current COVID-19 testing. You may have heard people come out and say, oh, well, I tested positive for the disease, but then we went back and we did a couple other tests to make sure. And actually, I came back testing negative. It turns out I don't have the disease. You've seen that actually in the NFL. The Indianapolis Colts last week had that issue where like 4 people on the team tested positive for the disease, and the NFL was ready to postpone their games and shut down their organization for a couple of weeks. But they retested them multiple times, and they found out all those tests were what is called a false positive. So that one is actually an interesting conundrum. It turns out that when you go get tested for COVID-19, the test is not going to be 100% foolproof. It's not going to be perfect. There's going to be a possibility of a false positive where the test tells you you have the disease when you actually don't. And then there's also going to be the possibility of a false negative where the test comes back and says you don't have the disease, but you actually do. A false negative is worse than a false positive in this case because a false negative then makes you feel secure and comfortable in going out and hanging out with people without a mask or something when in fact you have the disease and you could be spreading it to them. So this is a very important problem in medical science. It's very much a probability problem. It's very much something that statistics helps medical science in. statistical research can really provide a boon to this kind of thinking. So what this chart says is that, let's say we had a total number of people who were tested for the disease. Now, of those who actually truly have the disease, 20 of them are going to test positive for it, but 4 of them are going to test negative for the disease, which is not good. That's kind of scary. Of those who do not have the disease, and they used D complement, I wish it was DC Comics. Of those who actually truly don't have the disease, 8 of them are still going to test positive for the disease. 68 of them are going to test negative. So this right here, 20, and this number 68, those are correct test results. Those are test results that are actually accurate. But these down here, the 4 and the 8, are test results that are inaccurate. They are wrong. And just testing has that built into it. So 100 total people were tested for a particular disease. If a person is selected at random, what is the probability of selecting a person who tested positive for the disease, given that they actually have the disease? So we're given that they have the disease. So we are focusing in on this row. This is the row of people who have the disease. This is going to be, well, given that they actually have the disease, that means the denominator is going to be 24, the total number of people who have the disease. In the last table, the totals were given to you, which is nice. This table, they're not, but it's still implied. You got to add them. And then among those who tested positive, there were 20 who have the disease and tested positive. And so you can reduce this as you see fit. It reduces to the fraction 5/6, which is 83.3333% or 0.833333. Down here, what is the probability that they tested negative for the disease, given that they actually do not have the disease? So now we're only looking at the people who do not have the disease. That's what we're given. 8 plus 68 is 76. So that's what that denominator is going to be. And then we want the people who tested negative for the disease within that group. That's going to be 68. So there's a 68 out of 76 chance that someone tested negative for the disease, given that they truly do not have that disease. Finally, what is the probability that the randomly selected person, so each of these is a new probability problem, you ignore the previous ones. What is the probability they don't have the disease, given that they tested positive? So we're just looking at now this column, the positive tests. That'll be our denominator, the total number of positive tests, which was 28. And then we want those who don't have the disease within that category, which would be 8. So I'm actually going to calculate that. It's about 0.2857. That's rounding. .2857. We'll move it over so you can see it better. So what this means, this is among the people who tested positive, this is the percent of them that don't have the disease, which means the false positive rate of this test, the observed false positive rate, is almost 30%. Almost 30% of people who test positive for the disease don't actually have it. That's terrible. That is extremely inaccurate. That is a very, very bad test. You need to get that false positivity rate well under 1%. And then you need to get your false negativity rate which is actually the worst case, you need to get that way down as well. But even the best tests on the planet for a certain disease are not 100% foolproof, always guaranteed to be accurate and have no false positives and no false negatives. But this is a very interesting thing. So if you've ever had a COVID test, or if you go get one, they'll say, "Oh, this first test is 80% accurate," but that's not good, first of all. And they usually just run that first test because if it turns out that you test positive for it, they're just going to assume you have it and not run any more tests, which I don't think is entirely fair. Now, one more quick example here. Let's use maroon. In 2007, 12.7% of all births were preterm. Also in 2007, 0.22% of all births resulted in a preterm baby who weighed 8 pounds 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds 13 ounces or more, given that the baby was preterm? So we're given that the baby is preterm. So our denominator is going to be the probability that the baby is preterm. We're going to need to express it as a decimal. So 12.7% is 0.127. On top, 0.22% of all births resulted in a preterm baby that weighed 8 pounds 13 ounces or more. So this is the percent of people or of babies, 0.22%, that were both preterm and weighed 8 pounds 13 ounces or more. So we want the probability that a randomly selected baby weighs 8 pounds 13 ounces or more, given that they're preterm. So this top number needs to be the number or percent of babies that were both these things, preterm and 8 pounds or 13 ounces or more, which is this 0.22%, which means, though, we need to express that as a decimal. So it's going to be 0.0022. And then we'll actually do this calculation. Let's see what we get. About 0.017. In other words, among babies who are preterm, about 0.017 of them are going to weigh more than 8 pounds 13 ounces, which is not a lot. And I believe 8 pounds 13 ounces is considered a kind of a healthy weight, although that may just be for male babies or something like that. So there you go. That's it for section 5.4. Now for section 5.5, this is going to be the last section of chapter 5 that we're going to study. And frankly, it's a bit of a doozy. It's going to be a lot. Let's just say that. It's a good way to say it. The reason it's a doozy is because we have to conquer all of these counting principles, certain counting principles that we're going to use in order to compute probabilities. Because it turns out some of the toughest stuff you're going to do is count. Some of the toughest things you're going to do is count, believe it or not. And it's because we're not counting things that are only going to be like, oh, it's going to turn out to be 11. We're going to start counting things that could take millions and millions of counts that could be that large. Um, so that is just going to kind of be where we're at today. And it's going to be tough to do some of these counting problems. So we're going to need to really pay attention and work hard together and all that good stuff. So the first thing we need to talk about is the fundamental counting principle. The fundamental counting principle. This is going to be kind of our guide through the Western lands. The fundamental counting principle is going to teach us how to count things. Specifically, it's going to teach us how to count things that occur in succession. So the way you do it is you have a number of items that you have to choose. So say you're going to the finest restaurant on the entire planet for a date. You're having a little date night. You go to the finest restaurant on all the planet, which is Chili's, and you're gonna sit and you're gonna order a drink, then you're gonna order an appetizer, and then you're gonna order the actual meal. So you gotta order a drink. You're gonna get yourself an appetizer. You're gonna get yourself some of that skillet queso, which I love, and then you're gonna order a meal. Well, let's say that Chili's happens to have 35 different drinks you could choose. That's pretty realistic. I mean, really, if you think about it, if they have a full bar, there's thousands of drinks that could be made at Chili's or at any bar, really, if you're drinking alcohol. The appetizer, let's say that they have 11 different appetizers on their menu. And then let's say they have like 56 different meals, or your main entree, I should call it. Meal slash entree, the giant. The number of different experiences, if you want to call it that, you can have, the number of different drink, appetizer, and entree combinations you can have, you're going to need to multiply each of these individual numbers. And you're going to end up with 21,560. That's pretty cool. There's 21,560 different entree or meal experiences you could have. If you went to Chili's every single day, which sounds like heaven to me. Of course, that's going to get awfully expensive, but you know what? It's worth it. If you went to Chili's every single day and you tried a different one of these experiences, so you start with one thing, then the next day you change out the drink, the next day you change out another thing. If you wanted to get all 21,560 different meal experiences at Chili's, it would take you over 59 years to experience all of them if you went once a day. So that's just kind of a neat little idea. I remember when Burger King released their, smartphone app, which everybody has to have an app. And I say app. I make sure that P is very pronounced. Otherwise, it just sounds like I'm saying like you're opening your mouth for the doctor or something. I remember when Burger King first came out with their app, they were so proud. There's 35 million different ways you can make a hamburger. And, people were skeptical and they said, Burger King, you lie. And it turns out they may not have actually lied, because if there's a lot of categories like lettuce or no lettuce, tomatoes or no tomatoes, pickles, you want that. Which condiments do you want? Ketchup, mustard, mayonnaise. More than, any two of those. What else do you want? Do you want, how many patties do you want? What kind of buns do you want? Cheese, all the things you can put on a hamburger. Do you want their Impossible Burger, their vegan burger they made? All these things, it actually could stack up really quickly. You got lots of numbers you're multiplying together, and they can add up quicker than you'd think. So kind of an interesting idea. Now, why do we multiply? Why do we multiply? Maybe it just kind of makes sense. Maybe it doesn't. But let's use a very simple example to demonstrate that. Let's say you have two pairs of jeans, light and dark, and you have three shirts that you're going to wear, red, white, and there's a missed opportunity to make that blue. So let's just make it blue ourselves. Oh, come on. I got to use the actual blue. I'm going to do that. There we go. Red, white, and blue. Maybe it's the 4th of July and you're feeling like going out and celebrating. So if you have 2 pairs of jeans and 3 shirts, how many different ways can you make an outfit? Where an outfit is you pick one of your pants and you pick your shirt. Now, in reality, an outfit could actually have a lot more categories than that. You could have a watch you're going to wear, a hat or not that you're going to wear, your what else? Your shoes. I don't know what else. Undergarments, things like that. That could be part of it. Um, but let's just keep it to 2 categories to keep it simple for this. So the pants, you can either wear light colored pants, your lighter ones, or your dark colored pants. Then once you pick your pants, there's 3 different shirts you could do. You could do red, white, or a blue shirt. But that exists for each of these. You could go down this path and say there was also red, white, and your blue shirt that you could have worn. And so suddenly there's a whole bunch of different connections you can make here. And so now we see there's 6 possibilities. You could do your light pants with the red shirt, light pants with the white shirt, light pants with the blue shirt, or you could have done dark pants with the red shirt, dark pants with the white shirt, dark pants with the blue shirt. There's 6 possibilities because what we're really doing is we're counting up 2 total groups of 3, 2 groups that have 3 things in them. But you remember the straight up definition of multiplication, at least the elementary definition of multiplication, is to count, it's the number of groups you have times the number of things you have in each group, assuming it's the same among all the groups, which it is here. Thus, you could write out all the possibilities and you can add them, or you can just say, I have 2 ways I can choose pants, 3 ways I can choose a shirt. 2 times 3 is 6. So there's 6 total outfits. Now, of course, this is just a simple one. In reality, you might have 20 different pairs of pants or shorts that you can put on, and you might have 40 different shirts. I don't know what your wardrobe looks like. I'm a man, so my wardrobe is a bit, limited because I don't care as much. Maybe, I don't know, maybe some women don't care about their wardrobes either. Some do. But anyways, so those are kind of the possibilities here. And of course, there's more categories. So if you actually had 5 total categories, let's say you had pants, shirt, shoes that you wanted to wear, maybe maybe you have some jewelry, rings or earrings, or some ice around your neck, a nice chain if you like that. And then maybe you have a hat that you're considering. There's 5 categories. You would just take the number of things in each of the 5 categories, multiply them all together. So you'd have 5 total numbers to multiply out. So that's kind of a justification for why we multiply. Why we multiply. Now let's go back in time maybe to simpler days when we would eat in a cafeteria. If you had 5 choices for a main course, 6 choices for vegetables as your side, 4 choices for a drink, and 3 choices for dessert, the total number of meals you can make is 5 for the main course times 6 for the veggies times 4 choices for the drink times 3 choices for the dessert. Let's see if I can do this one in my head. 5 times 6 is 30, times 4 is 120, times 3, there's 360 different meals that you could choose. And of course, that your choices are a bit limited in a simpler cafeteria. If you go to Chili's, you have tons and tons and tons and tons of choices. I mean, earlier, I probably lowballed the number of drinks you could get. I probably lowballed the number of meals you could do. And if you're doing all kinds of weird substitutions with your meals, you could get even more possibilities. And if you're wondering, Josh, you keep talking Chili's up today. You know, what's up? It's because I'm being paid by Chili's to endorse them. That's not true. That's a joke. I'm not being paid by Chili's. A pizza can be ordered with 2 choices of size. Maybe you get medium or large, 3 choices of crust, 5 choices of toppings. How many different one topping pizzas can be ordered? So it's going to be 2 times 3 times 5 in this particular case. Now, the problem actually gets a lot more complicated when you get to have 2 topping pizzas, believe it or not. And we, at this stage, we won't quite deal with that. 2 times 3 is 6 times 5 is going to give you 30. There's 30 different pizzas that you could choose. You're taking a multiple choice test with 6 questions. Each question has 3 choices. How many ways can you answer the questions? In other words, how many different tests could you turn in that have different answers? Well, there's 6 different questions. 1, 2, 3, 4, 5, 6. Each of those questions is going to form like a category here. And each of those has 3 possible choices because that's just what it tells us. So what's interesting about this one is you're just doing 3 times 3 times 3 times 3. Of course, we've had other math before. It's assumed you're walking into this class armed with some strong prerequisite math knowledge, and we know that's just the exponent, 3 to the 6th. 3 to the 6th, which, maybe I don't want to do that one in my head. 729. There's 729 different tests you could turn in, different ways you can answer your test. So this is creating some pretty interesting. What if you could leave an answer blank? So what if you just leave some of them blank? That one's actually kind of interesting. I'll just do this here. If you could leave some of them blank, then actually on each question, you have 4 possibilities. One of the 3 answers or the 4th possibility, which is to leave it blank. So in that case, you actually have 4s across the board. You have 4 in each case. Earlier, we had 729 different tests, but basically just by adding a 4th option on each question, this now becomes 4 to the 6th power. And again, I'm not going to do that one in my head. You don't have to either. You get a calculator. This is one of the few classes where I say go wild with the calculator and use it as much as you can. Almost no other class will I say that in because you got to actually learn the math behind it. But in this class, I'm confident in just saying, well, I'd rather you learn the process and the interpretation of the data and calculated numbers. So just by adding a 4th option to each of the questions, we go from 729 possible tests we could turn in to 4,096. That's, almost 6 times as many exams that we could take. So that's cool. Kind of a neat idea here. I mean, you can create a lot of these kinds of counting problems very quickly. A garage door will open with a 4-digit code entered into a keypad. So how many codes are possible? Well, there's 4 digits, so there's going to be 4 basically categories, if you will, or 4. I call this the slot method. I create 4 slots that represent the 4 choices I have to make. I have to make a choice for the first digit, the second digit, the third digit, and the 4th digit. And now if each of the digits can be 0 through 9, then that's actually 10 total digits if you count 0 with it. So each one of these has 10 possibilities that you can choose for. 10, 10, all the way down the line. which is going to be 10 to the fourth power, which you might recognize as 10,000. You might not need a calculator for that one. So there's 10,000 different possible codes you could enter. That's actually why passwords offer you some security. It's because there's so many different possible passwords you could have, or in this case, passcodes that you could have, that someone just trying to guess it at random is almost certainly not going to get it. And if you think about like passcodes, you know, whenever they tell you to use an uppercase letter, a lowercase letter, an exclamation mark, you know, or some kind of symbol. I mean, those kinds of passwords, if you could have anywhere from 8 to like 15 digits in your password, that could be trillions. That could be trillions of possible passwords, maybe even more than that, maybe quadrillions or quintillions, like a hilariously massive number of different passwords you could have. I mean, imagine you had a 9-digit passcode here. That would be what, 1 billion different possible passcodes you could have if you can have 9 digits. And so that makes it virtually impossible that someone's just going to random guess your password. Now, that doesn't mean that hackers won't try, but they use different methods. They use some deep magic from the dawn of time that is very complicated. It's also why password screens will lock you out if you try too many wrong passwords. Like if you do 5 wrong passwords in a row, it's guessing that you're some kind of hacker or some kind of person trying to get in when you're not allowed to, and it's going to lock you out, because if you were allowed to just keep guessing and you had a system for doing that, you would eventually get it. Now, old school, like in the 90s, before they had those kinds of security measures on, hackers would use computer programs that would input all those different passwords, because if there's billions of possibilities, a computer hacker is not going to sit there and type them all out personally. But if you let a computer do that, generate all the possible passwords and try all of them, and somehow do it in a quick way where they could take like a millisecond to do each try, eventually they could get in. But that's how, so we only allow like 5 possibilities before you're locked out, and that's for that reason. What is the probability of entering the correct code on the first try if you can't remember it? So in other words, you randomly pick a code and try it out. Well, there's 10,000 possibilities. You're only going to get 1 crack at it. So you have a 1 in 10,000 chance. Pretty minuscule, pretty tiny chance that you're going to correctly guess it on the first try. So that's pretty interesting, I think. Let me pull up our next little mini PowerPoints. This section is broken up into a lot of different PowerPoints. Let's see, what is a good one to do? The next thing I'll go over real quick. I'll just kind of go freehand with this one. I don't like this set of notes in particular. The number of ways you can arrange a certain number of objects. So this is still in section 5.5. Imagine you had 3 books. Imagine you have 3 books you want to arrange on a shelf, not a set of. You have Harry Potter and the Sorcerer's Stone, which was called the Philosopher's Stone in England, which is actually what it should be called, because a Philosopher's Stone is based on actual kind of old school fantasy alchemy. Anyways, you have Harry Potter and the Sorcerer's Stone. You have Harry Potter and the Chamber of Secrets. And then you have Harry Potter and the Prisoner of Azkaban. So maybe it's the year like 2000 and you're in between, the third book just came out or something like that, and the fourth book isn't out yet. Now you want to arrange them on a shelf. Now, obviously, the correct way to arrange them is to go in order of chronological order that they were written, which is already written here. But let's say that you were just feeling bored, maybe it's raining outside, and you actually wanted to calculate all the number of ways you could rearrange the three books on your shelf. So just to keep it easy, I'm going to assign quick letters to represent these, A, B, and C. So the different arrangements. You could do this. You could do ABC. You could do Sorcerer's Stone, then Chamber of Secrets, then Prisoner of Azkaban. And that's the right arrangement, but whatever. But let's say you're bored. You could do ACB. Now you've already done the possibilities with A in front. Now you could do BAC. You could do BCA. You could do CAB, and then finally you could do CBA. You could do them in reverse chronological order for some reason at that last one. And if you can think of another arrangement, another different way to order them, oh no, it didn't like that. Anyways, if you can think of another arrangement for that, then, have at it. But I can't think of another arrangement for these things. So it turns out there's 6 ways to arrange that. 6 total reordered arrangements. So 6 total arrangements, or another word for it is orderings. Well, the problem then is, once the 4th book gets released, it actually becomes, for those 4 books, there's a much greater number of arrangements. And then the 5th book gets released all the way up to there are 7 total books in the series. And so what I'm going to tell you backhandedly is that there's 5,040 different ways you could arrange all 7 books in the series if you wanted to play this little game with it. So you're not going to, it's not practical for me to write out all 5,040 possible ways you could arrange 7 books. So it's pretty clear that the more number of things you're trying to arrange, you're just going to need a different method. You're going to need a better method to actually calculate that. Well, let's use multiplication principle. Let's use multiplication principle. And let's say you actually had all 7 books here. You had Goblet of Fire. You have Order of the Phoenix. You have Half-Blood Prince, not Brood, Blood Prince. And then you have the Deathly Hallows. Those are the 7 Harry Potter books. The number of ways you can arrange those 7 is actually going to be kind of cool. We're going to use 7 slots here that I call them. You have 1, 2, 3, 4, 5, 6, 7 here. Well, let's see. You have 7 possible ways you can put them. The very first book that can go there, you have 7 choices for them. One of these 7 books here. So you have 7 choices you can put in the first position. But then once you've picked one of those books, you only have 6 left that you can put into the next position. And then once you've picked 2 of those books, you only have 5 left that you can put in the next position. Then 4, 3, 2, and finally 1. And we would multiply all of these things together thanks to the fundamental counting principle that we've already discussed. And if you do that, you're going to get 5,040. 50, 40. So 5,040 different arrangements for just 7 books. Well, it turns out that this little computation we did here is actually something really cool. This is called the factorial. Factorial. And it uses the exclamation mark to symbolize it. The way we do it, we would say that this is 7 factorial, 7 with the exclamation mark. So if you've ever seen that exclamation mark and it's in math, it's not, you're not shouting 7 really emphatically, you're saying 7 factorial. You literally say 7 factorial. And what it means is to start with 7, then multiply it by the next number down the line until you get to 1. The factorial tells you the total number of ways you can arrange n objects. The total number of different ways you could reorder them. And you might not think that's important, but we're going to see probably next class, we're going to see some reasons why that actually is a lot more important than you'd think. So for instance, if you want to know, you have 10 family members lining up for a photo, how many different lineups can you make? Well, that would be 10 factorial, which is 10, and I'm going to have to give myself more space probably. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now you could go into a calculator and just type that out manually. 10 times 9 times 8 times 7. You would get 3,628,800. There's over 3.5 million different ways you could rearrange your family members in a photo. So if you wanted to take a photo of each possible arrangement, it would take over 3.5 million possibilities, which of course is just absurd. That would take you 1,008 hours. That would take you 42 days to get every one of those photos if you were able to take one photo every second, which is not going to happen. It would take you 42 days if you were nonstop taking photos, one a second with no break. It would take you 42 days to get all of those. That's ridiculous. And it's just clearly not going to happen. A few quick notes. We're going to define 0 factorial and 1 factorial. You would think that 0 factorial is going to be 0. You're actually going to be wrong. 0 factorial is going to be defined as 1 because the number of ways you can arrange 0 objects is to not even do it at all, which is still a way, which is still an arrangement. It's a lack of arrangement. It's kind of the thought behind it. 1 factorial is also 1. You can't take the factorial at this stage of the game of a decimal number. 2.5 factorial is not going to mean anything to us. It turns out you actually can do it, but it's something else. It's something else entirely. But you can do 2 factorial. 2 factorial would be 2 times 1, or just 2. 3 factorial would be 3 times 2 times 1, which is 6, which we already knew. 4 factorial is 4 times 3 times 2 times 1, which is 24. So the factorial can get really large really quickly. 10 factorial is over 3.5 million. 11 factorial would be to take this number and multiply it by 11. So it only gets kind of more and more massive. It starts to balloon out of control. So finally, the last thing we're going to look at here, we're going to look at ways that we can make what we call subgroups. And there's a number of different subgroups we can make. So actually, I'm sorry, we need to look at this one here. There we go. So we already learned what the factorial is. We're going to learn what a permutation is. We're going to learn what a permutation is. A permutation is going to be an ordered arrangement of objects where a known item is used more than once and the order makes a difference. 4, 3 is different from 3, 4. If you put the number 4 before 3, it's different. We're also going to later learn about a combination where the order of the objects doesn't matter. We don't care what order they come in. So for instance, if you were making pairs of students, if you were pairing up, making different groups of students, then if you have a group that has Janie and John, it doesn't matter which order you present them. Janie John is the same as John Janie because it's just a pair of two. Who cares what order you present them in? It's still that exact pair. However, if you were talking about the president and the vice president, and whoever's name you said first is going to be the president, whoever's name you say second is the vice president, then the order does matter. Janie John means that Janie's the pres, John's the vice pres. John Janie means that John's the president, Janie is the vice president. So it just depends on the context of what you're talking about. A permutation says the order does matter. But a permutation actually goes even further than that. There's something cool about a permutation. So whenever you're just rearranging the items on a shelf and using a factorial, you're actually doing a permutation in general. You're saying for all 7 items I could put on the shelf, I'm going to find the number of ways I could rearrange all 7 of them. But what if you had 7 Harry Potter books and you only wanted or only could, you only had space, put 4 of them on the shelf? Let's say you also care about the order that the 4 appear on the shelf. How many arrangements are possible then? Well, now, instead of having 7 total slots, we only have 4 because we only have 4 spaces on the shelf. But the number of things that can go in space 1 is not 4, it's 7. It's going to be 7 because there's 7 things I can put on that first shelf. There's 6 then, once I've picked something to go in the first position, there's 6 books that can go on the next shelf, 5 that can go on the next shelf, and 4 that can go on the last position on the shelf. So it almost looks like we took 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, and it almost looks like we divided out by the factorials that didn't make it. So this turns out to be 840. So there's 840. In other words, there's 840 different ways we can select a group of 4 from a larger group of 7 where the order of the group of 4 matters. That's what this means. Where the order of the group of 4, so not only is this the number of ways I can make a group of 4 out of 7, it's also going to count up all the different ways I can rearrange those 4 objects. The order matters in that case. And that's actually how we're going to define a permutation here. It'll have to be next class, but that's how we're going to define a permutation. It's going to be the number of ways I can make a subgroup of a certain size where the order matters. And that's all there is to it. So we will revisit that concept next class. Let me take attendance real quick. Let me take attendance. Go ahead and drop your name here.